fact that I think there's pretty much only two formulas for circles that people are.
Pi r squared.
Pi r squared.
So pi r squared or 2 pi r are the two formulas we have.
Okay.
Which one is the distance and which one is the area?
Pi r squared is the area.
Why? Sorry, that, I'm not asking for a
No.
derivation. What's a memory trick that can tell you that that's for area?
I don't have one.
Okay,
Because it's squared.
yes.
What is it?
Because it's squared.
Oh.
Square means area, cube
Okay.
means
That makes
volume.
sense.
And just a single, just like meters would be a length. Circumference is just a length. So it is 2 pi r. So Chloe, you
Yeah.
should have just gone with it confidently.
I know. I'm sorry.
It's okay. 2 pi r over the period. So it's the distance it travels in one circle divided by the amount of time it takes to go around one circle. So this is 2 pi times 3 meters divided by 7 seconds. And we get something absolutely spectacular. 2.8 437,661 2.69 units? Like you mean it.
Meters per second.
Yes. So we now have the speed, it now has just become a plug and chug. The tension, which was the original question. The mass, which is given. Times the speed of 2.69 meters per second squared, divided by the radius of 3 meters. Did you forget to square the speed?
I got 9.65.
That's what I got.
10.65?
9.65, yeah.
9.65. Units?
Newtons?
Like you mean it?
Newtons.
Yes. Now let's say that you blank. You're suddenly thinking, you're not thinking the fact that, oh, we found a force, it has to be newtons because we're dealing with all the SI units. We're dealing with meters and seconds and, I guess, and kilograms. You're blanking on the unit, so you can just pull it straight from here because that, we have a kilogram times, I got a meter per second squared divided by a meter, which is a kilogram meter squared per second squared over meters, which is a kilogram meter squared per second squared meter. So you're left with a kilogram meter per second squared, and that's fine. I mean, that's a legitimate unit there. It's just that that's also equal to a Newton. But some people will just leave it like that. Why not? All right, questions on this before I make it more difficult? All right, let's make it more difficult. Oh, by the way, this speed you can think of as distance over time. Angular speed, so this is speed, angular speed. Actually, quick side question. Oh, yes, Chloe.
I just had like a quick question about the omega. Is there like another, like, I guess, way that you could write it instead of a W, or the W, not a W, but like,
The omega.
yeah.
Instead of using the omega?
Instead of using the W, what looks like a W for omega? Is there something else that you could use?
Oh, so it looks less like a W?
Yeah.
Traditionally, no. I guess you could always make up your own and just define it at the top. Just so long as you keep track of it.
Okay.
How do you know this is speed and not velocity?
There's no vector over it.
Exactly. All right. So we get to chapter, I think it's 9, we get into it in more detail. But there's a rotational analog of all our linear stuff. Angular speed deals with, obviously, traveling in a circle. But instead of distance, it is the change in the angle over the change in time. So if I go through 360 degrees, I'm also going through 2 pi radians. How many of you dealt with radians? Okay. What's a radian? For the 4 who were willing to volunteer.
Radian complete. One time around the unit circle.
That's definitely not 1 radian.
Actually, and it's 2 pi.
It is indeed 2 pi radians.
Is that 6 radians?
It's 6.28 something. All right, let's do the quick lesson in radians. I have a circle. 360 degrees. Why are there 360 degrees in a circle?
Wait a minute.
Who? Who's responsible? Whom do we blame? I guess you haven't gotten to that video.
Is it the Babylonians?
Indeed, it is.
Aliens.
You remember? Yeah, well, besides the aliens. Where did 360 come from the Babylonians? Keep going, Sarah.
60 was religious, or it could be divided by multiple numbers could go into it.
Right?
And the perfect triangle has 60-degree angles. And then if you put 6 of those triangles together, it looks like a circle.
And there you go. So you end up with the 6 triangles. Think Trivial Pursuit. Is that reference to passing? Trivial Pursuit. I'm looking for some recognition here. I've got a nod, a shake, and mostly just looks. Okay. Trivial Pursuit. You got 6 wedges that all fit inside a circle. Anyway, I got 6 of them, 60 degrees at an angle because it's religious or perfect or something like that. I get 360 degrees. It's man-made or alien-made for those others. There's been a big push in math to get rid of all the man-made stuff. What is natural to mathematics that is just inherent in the way that nature's created? Well, there's one thing that all circles have in common. They all have a radius. So what they figured out was that if I take a radius here of a circle, and then I take that length, so imagine I got a string there, I take that length and I wrap it, that circle is just so horrible. Let's try that one. Not my worst, not my best. All right, somewhere around there. So I have my radius here. So imagine that's a string and you just wrap it around the edge here. So that this arc length here is r. That angle right there is the same regardless of what circle you're using. If I take the radius of any circle, wrap it around the edge, this angle that is subtended is always the same. And that they felt was natural. And so that is what they defined as a radian. 1 radian. If I wrap 2 radiuses, what would the angle be?
2 radians.
3 radiuses?
3 radians.
Not drawn properly, but close. So how many times is it around an entire circle? How many radiuses can I wrap around an entire circle?
6.
We can be better than that.
6.
6.
6 radians.
6 is close, but not quite the right answer.
2 pi?
Yes. You can get 2 pi of them. Right there, I get 2 pi radiuses around the circle. Which means I get 2 pi radians around an entire circle. Now the reason I'm going into this is that when you're talking about angular speed, you typically want it in radians per second, not degrees per second. That would be a real mess. The SI unit for omega is the radian per second, or for those who really don't like writing the word radian down, or the abbreviation. Now typically, you don't have to write radians. There is a relationship between arc length. So if I'm going around a certain distance, we'll use S for the arc length. There's some angle here, theta. The arc length is equal to the radius times whatever angle that's there. If this is in meters and that's in meters, theta would not have any units. So I'll sometimes refer to radians as the unitless unit because you don't actually have to write radians. But I recommend writing radians when clarity is required. Because if I write the angle as 5, technically it's 5 radians because they didn't say any unit afterwards. But it's possible that you meant 5 degrees and just didn't bother writing the units down. So you would write radians to say, hey, I know what the units are. Now, getting this relationship here. So if I want to find the speed of an object, as we did over here, it's the circumference divided by the period. Which is 2 pi over t times r. And 2 pi over t, well, that's the angular speed. Because if it goes around an entire circle, it's doing 2 pi radians. That's the angle that it goes through in the same amount of period, same amount of time. So that's omega r. And so we have a relationship here that we will use more than just today, that V is equal to omega r.
Can you go over that step again? You got rid of the R?
I didn't get rid of the r, I just factored, sort of brought it out. I guess the intermediate step is 2 pi over t times r over 1.
Okay.
So just breaking it up into the product of fractions. And then this is omega times r. Is that sufficient?
Yes.
Okay. Other questions?
According to the textbook, the omega r was the linear velocity, or linear speed. So, but are those interchangeable, or do we only use that for linear?
V is linear speed.
Okay, so what you just were breaking it down.
Showing the relationship between
Okay.
linear, for something that's traveling and that's rotating, showing the relationship between linear speed and angular speed.
Oh, okay, gotcha.
That's what I was shooting for.
Okay.
V.
V equals omega
I was
r.
gonna say, so linear speed equals the angular speed times the radius.
Yes,
Okay.
yes.
And so is it, because in the book it says linear velocity, so it'd be linear speed and angular speed.
If you want to throw in the relationship with, the trouble with angular velocity, so V, saying V equals omega r, angular velocity is, sorry, linear velocity is angular velocity times r. The directions get messed up, and so this is why this is misleading. So let's just talk a little bit about the direction and why I went with the scalar form and not the other one. If I'm swinging this around, I have a stopper that's traveling in a circle using angular speed or angular velocity has some merit here. The question is, what is the direction of the angular velocity? Angular velocity is a vector, it's got to have a direction. How would you describe the direction of the spin? Did you say straight?
Yeah.
You said the angle of the spin? What did you say?
No, the direction of the spin.
The direction of
The direction of the angular velocity. So let's do it this way. So how would you describe this, the direction of the spin of the stopper?
Towards the center of the rotation.
That's the direction of the force, not the spin
Counter-
itself.
Is it going counterclockwise? Is that right, the counterclockwise direction?
It's clockwise to me.
Oh, yeah.
What, 90 degrees?
90 degrees.
I don't know.
Sounded good.
But what Chloe mentioned, the fact that clockwise or counterclockwise, this is a problem. Because if I were giving you a problem and I said something rotating counterclockwise, from whose point of view? Now, usually it's from the point of view of you're looking down at a piece of paper for a test. But here, if you need to describe to someone outside of this room, well, if you're sitting in the middle of the room, it's spinning counterclockwise. If you're at the board looking down towards the middle of the room, it's clockwise. That's a lot of words, and physicists really don't want to do that.
So you say you're like facing east, it's spinning a certain, or like, would you
Well,
specify the direction you're facing?
we now use the right-hand rule. There are a lot of right-hand rules in physics, all stemming from basically cross products. But the right-hand rule is for something that's spinning, you put your thumb, treat your thumb as an axle. So it's this thing is spinning like this. It's like you have an axle right there in the center. So my thumb's either pointing towards you or towards me. And then you want your fingers to curl in the direction of movement. So it was spinning around like this. So I put my right hand like that. My thumb is pointing to the back of the room. And so the direction of the angular velocity of that stopper was that way, towards the back of the room. Or now you could actually say, I guess that's west-ish. So if you said the angular velocity of the stopper was west, it has to be spinning like this. You don't have to describe your point of view. All you're doing is just, you're using a reference that a compass can tell you. So, if I spin this over my head, what is the direction of the angular velocity? And
Down.
I was gonna say up. If you put your,
All right.
and you curl your fingers like this.
it is either up or down. It is not back or forward.
Oh,
Oh,
You're backing down from your down.
I think it's up, but I don't know why. I'm just
The
doing
right
it.
hand rule.
Let's see if I can.
Put your thumb as the axis and you curl your fingers.
Yeah, it's spinning around like this, so if I curl my thumbs like that, my thumb points up. The angular velocity was up. At the moment that it was here, when it's spinning around, the moment it's here, what was the direction of its linear velocity? And its angular velocity was that way. They are perpendicular to each other.
That's what I was thinking of 90 degrees. So
Ah.
is angular or linear? Linear is 90 degrees, typically.
What is it?
But they're separated by 90 degrees.
Okay,
Or-
that's what I meant. Like, yeah, like your resultant or whatever, where if the directions are going like this, then it's gonna go 45. Is that?
You lost me there on that one.
I was just.
No matter how it's spinning, the linear speed and linear velocity, angular velocity will be 90 degrees apart from each other. I'm not sure where the 45 popped into it.
Okay, I'm not sure if I can explain it either.
Okay. Well, in the middle of the night, when you have that horrible dream, you suddenly realize what it is. Just call, leave a message on my phone in the office.
Tiffany.
Oh, that was unfortunately filmed. All right, there we go. Now, why I brought this in? one, it's gonna be handy in what we're about to do, but also take a look at connecting these two equations right here. My centripetal acceleration, v squared over r, and that was not the marker I wanted. V is equal to omega r. And so that's equal to omega squared r squared over r. And one of the r's cancels out, and I'm left with omega squared r. So the question that some students have is, all right, I'm given a centripetal acceleration problem. I got something that's traveling in a circle, so immediately you should be thinking centripetal. Which one do you use? Do you use v squared over r or omega squared r? It depends what you're given. It depends what's going to make life easier. So let's bring the stopper swinging through the air in a horizontal plane, except this time we'll throw gravitational forces into it. If I'm swinging this with gravitational force, what's going to be different between what we just did? Without a gravitational force, we just did that problem. If I throw gravitational force into it, what's going to happen?
It's gonna pull it down. It'll pull it down.
You said pull down? Yeah. So the swinging, the circle, is basically, it's going to be, here. Put some angle theta here. Where, in which direction, so it's spinning around in a horizontal circle, in a circle in a horizontal plane. In which direction is the centripetal acceleration?
One more time, say?
Actually, let's go through the process. Let's do, I know some people just pointed in the direction, but let's not skip the step yet. The force diagram. So F tom. What are the forces acting on the stopper?